All right, chemistry, we're going to continue with the answers video for the day 27 lesson, solutions 2. And so we'll go on to problem 2A. So we did this one in class, and let's go ahead and do it here. So what is the molality of lead ions in a solution that is 400 parts per million ppm of lead ions? Okay, so what we're going to do is let's get the definition of molality. So molality is moles of solute. In this case, it's lead for over kilograms of solvent. So compare it to molarity. Molarity is also moles of solute up on the top in the numerator. The difference is molarity is liters of solution and molality is kilograms. That's a weight of the solvent. In this case, in almost all cases, that's water, H2O. So it's different denominators. Okay, so we're going to go ahead and write that over here. Okay, so moles of the solute, which is lead, in the solvent, the substance that does the dissolving, and that's the water. So it's kilograms of water. Okay, 400 parts per million. So parts in the context of chemistry in this case means grams. You could think it might have meant moles, but it's actually grams. And it's per million. So what it's saying is there's 400 grams of the solute, that's lead, for every million grams of the solution, of the solution. So it's not of the solvent, the H2O, it's of the entire solution, the lead and the water together. So let's write that over here. Okay, where do we get that from, by the way? How did we know that? Well, if you come over here to mass percent, it's grams of to parts per million. There you go, parts per million. It's grams of solute over grams of solution. So it tells you that right there in case you didn't know that. All right, so now what we're going to do is we need to break the problem into two parts. The top part, so that's 400 grams of lead, and over here we have moles of lead, moles of Pb. So we need to get from grams to moles on the top. So we treat that as a separate problem. Next, we then go down to the bottom, and we need to get from 1 million grams of solution to kilograms of water. All right? So again, you break the top into one problem, break the bottom into a second problem, and you just put them together in the same equation. Okay, so the first one is to get from grams to moles. So that should become familiar to you by now. It's a molar mass conversion. And all we have is lead. We don't have a compound here. It's just a single element. So we're going to write it down here, kind of get it out of the way. 1 mole and for lead from the periodic table, it's 207.2. We don't need to add that to anything. That's all it is. It's just lead. Okay, so that's our equivalency that will get us from grams of lead to moles of lead. So we're going to draw a box here. Okay, so which one of these two goes on top? Which one goes on bottom? Well, we need grams to cancel out and moles to appear on the top. So we're going to put grams down at the bottom. And we're going to put the moles on the top. And the last man standing on the top is the moles of Pb. So we're done with the top. We don't need to deal with this box anymore until the very end of the problem where we need to use the 207.2 to calculate our final number. Okay? Now what we're going to do is we're going to go down to the bottom. And we need to get from 1 million grams of solution to some number, 2 kilograms of H2O. So this presents two things we have to do. We have to get from grams to kilograms. Well, that's pretty easy because we have this conversion right here that I'm circling. I put it up in the heading of all the pages, the big 3 conversions. So getting from grams to kilograms is easy. It's just that step right here. The tricky part of this problem is getting from solution to water. So that's going to be a little trick here. So let's see how we do that. We do that first by remembering that the solution here, what we've been calling SOLN, is really the grams of solution is equal to the grams of the two things that make up the solution. What is that? Well, PB is one of them, plus the other one, which is grams of H2O. So we're going to break the solution into what makes it up, which is grams of PB and grams of H2O. So I want you to see the logic here. We know grams of PB. It's right here. We put it up here on the top. We just crossed out the grams, but it's grams of PB is 400. There's 400 grams of PB. And we know that there's 1,000,000 grams of the solution. So if we know this number right here, the grams of solution is 1,000,000. If we know the grams of PB right here is 400, then the difference between those two is going to be the grams of water. So it becomes a subtraction problem. So grams of water plus 400 equals 1,000,000. So we're going to do that as a subtraction problem. So 1,000,000 grams of the solution, these two together are the solution, minus 400 grams, which we know is the lead, and that's going to give us the grams of water, and that number, just do it on a calculator, is this. Okay, it's going to give you 999,600 grams of H2O. Okay, so we know the grams of H2O. So we need to get from grams of solution to grams to kilograms of H2O. So if you look at this, there's a relationship here. We know that for every 1,000,000 grams of the solution, the PB plus the H2O, we're going to have 999,600 grams of H2O. So that becomes an equivalency for us. In fact, we can write it down here below. Again, solution being these two together, because we know that every time we have 1,000,000 grams of solution, we're going to have 999,600 grams of H2O. So that becomes an equivalency right there. So now we're going to draw a box. And which one goes on top, which one goes on bottom. Again, we're not paying any attention to this box anymore. So we're starting with grams of solution. We need to get H2O down on the bottom. So we're going to go up here and we're going to put 1,000,000 grams of solution over this number. Okay, so grams of solution here cancels with grams of solution there. And so now on the bottom we have H2O instead of solution. That's what we needed to do. We needed to get the correct substance, H2O, H2O. So the only thing left to do is we have grams here and kilograms here, so we need to make the conversion between grams to kilograms, and that's this one right here. So we've used that one before. That's a simple one. So I'm going to put a time sign here in a box. So we need to get grams to cancel out. It's on the bottom here, so we're going to put it on the top here. And it's grams of H2O. Be careful that you choose the right substance. It could be grams, 1,000 grams equals a kilogram of anything, but we're interested in H2O here, so we're going to put the H2O. And it's 1 kilogram. So grams of H2O, grams of H2O. So the last man standing on the bottom is kilograms of H2O, which is what we want. We already had the moles of PB on the top. So now what you simply have to do is, now there's one more thing you can do, you may have noticed. You've got 1,000,000 on the bottom here and 1,000,000 on the top here. So we're going to cancel those. We haven't done that before, canceling numbers like that, but it's so obvious and you don't want to have to deal with a number like 1,000,000 twice, so get rid of it. So it's going to be 400 times 1,000 divided by 207.2 divided by 999,600, and that will give us our final answer. Okay, and that gives us 0.0019, and that's moles of PB over kilograms, so that's molality. So really the way you would write a final answer, or it might appear on a standardized test, is 0.019, and then molality is just lowercase m, small m. Okay, I like this because it tells you exactly what you're dealing with here, but this is the way it would formally be written. Okay, so that takes care of 2A. 2B is exactly the same, except I gave you a different number for parts per million. Go ahead. So the way to approach this is, if you really are serious about learning these, is study this. Be sure you understand each step. Kind of try to memorize each step that I did. It's a lot. There's a lot here. Try to do that and then cover this up and go down and see if you can do the problem by yourself. And if you get stuck, then just uncover it and see where you're stuck. But once you see that, cover it back up again. Keep going. See how much of the problem you can do on your own. You ultimately have to be able to do a problem by yourself. Okay, problem 3A. And it says, what is the mole fraction of sucrose in a solution that is 5.84 molal sucrose in aqueous solution? We mentioned what aqueous solution means. It means that the solvent is water. And it almost goes without saying that we're almost always dealing with aqueous solution. We always have a solvent of water, okay? So, but that is what that phrase means. Okay, so what are we looking for? Mole fraction. So we come over here, and there's mole fraction. Now that's the Greek letter chi, C-H-I. I think it's C-H-I. Anyway, it looks like an X, a scripted X, but it's chi. And that represents mole fraction. So it's the moles of one solute, in other words, implying that there might be more than one solute, but in our problems there is not. There's only one solute. So the moles of one solute over the moles of all solutes in the solvent. So everything, as you can see from this, has to be in moles, okay? So let's go ahead and write this equation, this general equation, on our sheet. So the mole fraction of this chi, Greek letter chi, equals moles of the solute, and the solute is sucrose. It's C6H12O6. But rather than write that big long thing, I just call it SUC, sucrose. Okay, that's good enough. It identifies it, okay? And that's going to be over the total moles of everything that's in that solution. So that's going to be, again, moles of sucrose plus moles of H2O. Okay, so what we need to do in order to get our answers, fill out these, find out what the moles of sucrose and the moles of H2O are, okay? Well, it says it's 5.84 molal. Now, we're not going to do this problem in a nice straight line from beginning to end. This problem doesn't quite work that way because that has a plus sign thrown in there in the denominator. But let's figure out how many of these we can figure out here. So moles of sucrose. So it says molality is 5.84. It's moles of solute, okay, from our previous problem and from your sheet. Molality is moles of solute over kilograms of solvent, which is the water. Okay? Okay, and this means for every 1 kilogram of water. Okay, so we have 5.84 moles of sucrose for every 1 kilogram of water. So we know the moles of sucrose right here. It's there and there. The only thing we got to find out is the moles of water. So we have this much for every 1 kilogram. So we have to figure out how many moles is 1 kilogram of H2O. So we're going to go down and do a separate equation down here. Okay, and what we want to know is moles of H2O. That's what we're trying to find out. And what we're starting with is the denominator here, 1 kilogram of H2O. Okay, so we know molar mass for water is this. There it is. Okay, so first we got to convert kilograms to grams. If we're going to use this molar mass equivalency, we got to convert kilograms to grams. So let's get from kilograms to grams. So we know the conversion is there's 1,000 grams of H2O over 1 kilogram of H2O. So kilograms H2O cancels and cancels. Okay. I still didn't leave myself enough space. So now I have grams of H2O, 1,000 grams of H2O, and I have a conversion to moles right here. It's 1 mole of H2O equals 18.02 grams of H2O. So I'm going to turn that into a conversion factor. I'm going to put moles on top because that's what I want to know is moles of H2O. Okay, so grams of H2O up here cancels with this down here, and I end up with what I needed is moles of H2O. So the equation is saying 1 times 1,000 times 1 divided by 1 divided by 18.02. So basically it boils down to 1,000 divided by 18.02. And when you do that on your calculator, you will get 55.5 moles of H2O. So that's how many moles there are in 1 kilogram of H2O. So now we have moles of H2O. We already have moles of sucrose right there. So we go and plug them into this formula. And I'll just put moles, and they're all going to cancel out. So a mole fraction doesn't have any units. It doesn't have any dimension. So So there's moles of sucrose on the bottom. And moles of H2O we just calculated. So let me show you how you do this calculation. You're going to divide this by these two things put together. But remember, a calculator wants to do a division. It does PEMDAS, order of operations. It wants to do divisions before additions. So let me show you how I do this. Right here. It's 5.84 divided by, and now I've got to put this addition in parentheses. Otherwise, if I do 5.84 divided by 5.84 plus 55.5, it's going to divide 5.84 by 5.84 and get 1, and then add it to 55.5. So I have to put this bottom, this denominator, in parentheses. So there it is. And close the parentheses on the, and what I get is 0.095. And there are no units to a mole fraction. What it's saying is that 0.95 of the solution is sucrose. So the rest of it would be water. Now, it's not a percentage, it's just a fraction. They call it a mole fraction even though it ends up as a decimal number. Okay, so again, take a look at that, study that, and then do 3B. Okay, we move on to problem 4A, and this is a dilution problem. Those are actually the easiest ones. So if 1.5 liters of 5 molar solution sodium chloride is diluted to 6 liters, what is the molarity of the new solution? So dilution means you add water. This is I made the lemonade too strong. I put too much powder in. It's too sweet. It's too syrupy tasting. So I'm going to add water so it tastes right. Okay? So the formula for this, very simple, is this. It's M1 times, and I asked you to correct this down here, it's times V1. So it's the molarity before you added the water times the volume before you added the water, M1 times V1 equals M2 times V2. So it's a pretty simple little formula. Okay, so what is our M1, V1? What is our volume and molarity before we add the water? So it's 1.5 liters is the volume. And the molarity is 5 molar, so 5. Okay, and that's going to equal, it's diluted to 6 liters. So now you have a volume V2 of 6 liters. And what you want to know is what M2 is, what the new molarity is after you've added the water to make it 6 liters, okay? So 5 times 1.5 is 7.5. Don't really worry about the units of measure because molar is going to cancel with molar and liters with liters. And I take that back. The molar is not going to cancel, but the liters are going to cancel. You're going to end up with molar for M2. So it's 7. 5 times 1.5. And then you divide both sides by 6. So if I do 6 there and divide by 6 there, this cancels, and so I'll actually come over here and write it over here. That's going to give you 5 times 1.5, and when I said 7, that was wrong anyway, divided by 6, okay, just an algebra problem. So 5 times 1.5 equals 7.5, and you divide that by 6, and when you do that on your calculator, you get 1.25 molar. Okay, so that's how you do a dilution problem. They're fairly simple. Okay, all right. Do 4B. I'm going to move on to 5A. All right. So we have. Now I wanted to point out I did this in class. This is just a reference to me where I got the problem. This is Brown, LeMay, Burston. That's the AP chemistry book. That's a college chemistry book, and it's on page 544. So you're, in your 6th week of learning chemistry, you're already doing problems from the middle of a college textbook, okay? And this isn't even the hardest problem you've done so far. So anyway, just kind of stay focused on this and you will learn it. So a solution is made by dissolving 4.35 grams of glucose, that's this, in 25 milliliters of water at 25 degrees centigrade. Calculate the molality. So we're trying to find molality. Now, students sometimes see this and they wonder, well, what's that have to do? Do I have to put that number in somewhere? And the answer is no. 25 degrees centigrade, we haven't talked about temperature yet in this class, but it's roughly room temperature. So it means that it's at pretty normal temperature. It's not some unusual temperature. So the answer is you really don't do anything with that. It's just telling you it's kind of done at normal room temperature. Okay, so molality, again, we go back to our sheet. Molality is moles of solute over kilograms of solvent. So we're going to come over here, way over here on the right, and write that. And the solute is the glucose, this, but rather than writing that formula every time, I just call it GLU. We just call it glue. And the solvent is H2O. Okay? So what they said you're doing is you're taking 4.35 grams of glucose and you're putting it into 25 milliliters of H2O. So let's come way over here and write that. So what we're going to do is, I see that if I have grams of glucose on the top, I can easily convert to moles of glucose using molar mass. And if I have milliliters of water on the bottom, then I can convert that to kilograms of water. So what am I going to do with these two numbers? And this is where you have to develop just a little experience doing this. I'm going to put them one over the other. I'm going to put this one over this one. So I'm going to come over here. Okay, so once again, we break it into top problem, bottom problem. So we're going to start on the top. We need to get from grams of glucose to moles of glucose. So for that, we're going to need to have a molar mass. It doesn't hurt to compute that. So we have to have the molar mass for this, C6H12O6. So let's do that. C, you got 6 of those, times 12.01. H, you have 12 of those, times 1.01. And O, you have 6 of those, times 16. So this one is going to be 72.06. This one is going to be 12.12. And this one is going to be 96.00. And if you add all those up, you're going to get 180.18 grams per mole of glucose. Okay, so I'm going to come up here and I'm going to make a conversion, a molar mass conversion to get the moles. And I'm going to write on the top, I need grams to cancel out, so I need it on the bottom, so it's 180.18. And it's 1 mole on the top of glucose. Grams glucose cancels with grams glucose. And so we have moles of glucose here, and that's what we want in our final answer. So we're done with the top. We've taken care of the top. Okay, next up, we now need to get from milliliters of water to kilograms of water. So this one was easier than the lead one, the parts per million one, because we have H2O here and H2O here, so the substance is the same. We just need to get from milliliters to kilograms. So to do that, you have to remember one of the big 3 conversions that you use is from milliliters, not to kilograms, but to grams. It's this one right here. 1 gram of water equals 1 milliliter of water. So that's only true of water, of H2O. So we're going to come back down here and use that conversion. So it's times box, and I need milliliters of H2O to go away because I need to get to kilograms. So I'm going to put milliliters, 1 milliliter H2O over 1 gram of H2O. So milliliters H2O cancels and cancels. Now I have grams of H2O on the bottom. I need to get to kilograms. So we use another one of our big three conversions. It's 1,000 grams equals 1 kilogram. So I'm going to come back here. I need grams to cancel out. I have it on the bottom here, so I'm going to have to put it on the top here. And that's for every 1 kilogram of H2O. Okay, so grams of H2O, grams of H2O. So what I'm left with on the bottom is kilograms, which is exactly what I want. And we already had moles of glucose up here. So we're ready to do the math. I'll go ahead and put the answer down here just for space, and that will give us the molality of glucose. So it's going to be 4.35 times 1 times 1 times 1,000 divided by 25 divided by 180.18 divided by 1, and that equals 0.97. 0.97. There's the units of measure right there, but I'm going to change that to small m for molal. So it's 0.97 molal. Okay? All right, so I don't like videos to go more than about 30 minutes for a variety of reasons, so I'm going to stop this video and we'll pick up 6A on the next video.